Good morning, everyone. So we're going to pick back up in chapter 2. So today in chapter 2, we're going to talk about subatomic particles, how we can count protons, neutrons, electrons. Hopefully this is something you've seen before and is mostly a reminder, but we'll go through some examples of a couple of different elements. We'll generally look at a couple of different ions where we start to change electrons. You might remember we can make ions if we gain or lose electrons onto an atom. So we'll talk about coming up with the electron counts versus the proton counts for some ions. And then we'll get into some properties of elements in the periodic table, maybe do a couple demos, and then move forward into learning how to name some different classifications of compounds to kind of wrap the chapter up as we get into next week. As we look towards midterm one is a week from Tuesday, so we get all of next week to work on and finish chapter 2. And then Tuesday in recitations, we take the first midterm over chapters 1 and 2. You'll have a chance for a review. I sent an announcement about a review session Thursday night by one of our other chemistry instructors. If you're interested in that, definitely attend either in person. There's also a Zoom option. It'll be posted afterwards. And then I don't know how popular this will be, but I figure I can come in early before class for review time, Q&A, whatever, Monday before the exam next Monday. Not the coming Monday for Labor Day. We have Monday off. But the following Monday, I'll be here early, 7:15, for anybody who has questions. I'll have a few extra problems prepared if there's not many questions from the audience. So we can spend 45 minutes reviewing before the start of class. And generally, we're kind of moving on to new material the day before a test, which isn't maybe exciting news to hear that generally we have to kind of move on to be able to keep up so that we have enough time to cover the material ahead of midterm 2. But it's also, the department really wanted us to put the material we cover Monday on Tuesday's test. So it really took a lot of effort to not have that material on the midterm to begin with. So I'm glad that at least the material we have to cover Monday won't be on the test the next day so that you don't have to quickly learn it that fast. So that's kind of what we have ahead of us. A couple other reminders are there's daily quizzes. They're not for credit, but they're just for practice. If you haven't seen these yet, go to modules where you find the lecture slides. If you haven't found the lecture slides, just go to modules, lecture slides in Carmen. But there's also a daily quiz tab. And for most days of the week and sometimes over the weekend, there's some packets of quizzes. And these are, anywhere from like 5 to 15 questions, kind of depending on the packet, that give you a chance to do some review and to see how you're doing in the course. Gives you a chance to see some exam style questions so you can put yourself in exam mode. Exam mode's closed book, closed note. If we don't get a lot of practice in that kind of scenario, when we go take the test, that's when you tense up. You know how you tense up sometimes and you forget everything you know? It's really just because probably not enough time was spent practicing material with that type of advantage, with closed book, closed note environment where you're forced to recall that information. So just give yourself a bunch of practice on that end, as much as needed. You probably don't need to do every one of those quizzes I have posted, but I think if you do all the quizzes posted, I think you'll be good to go. So if you need them all, they're all there. Okay, so back into this question here. How many protons, neutrons, and electrons do the following contain? And so let's just remember right off the bat that our protons are a positively charged particle, and the neutral particle is the neutron, so no charge on the neutron, and then our electrons are the negatively charged particle. And then let's also remember that the protons and the neutrons, these are the particles that carry most of the mass. So the sum of our protons and neutrons, this is what we call the mass number. So the mass number is the sum of the particles that carry a majority of the mass within the atom. The electrons carry such a small amount of mass, they don't get counted into the mass number because the electrons are really light. And then we see the protons and neutrons being more massive, collect in the nucleus, and then the electrons are outside the nucleus, spinning around things that we'll describe as orbitals, and we'll talk about those later into the course. And so if we're looking at chlorine here, chlorine 35, there's two ways I can show the mass number. I can either put the mass number as a superscript here, and so the 35 on chlorine means that that's the mass number. And I can also write the element name dash, and then the dash is also the mass number. So we can say chlorine dash 35, that's one way of saying chlorine with a mass number of 35. And we can also say 35 chlorine with the superscript, that's another way of implying that that's the element in the specific isotope that we're talking about. So for this particular atom, we can count up the protons And neutrons, we want to look at chlorine's placement on the periodic table. That's really important. So chlorine's the 17th element. So that defines what chlorine is, and that defines the number of protons in the nucleus of a chlorine atom. So an atom with 17 protons is defined to be chlorine. If we had 16 protons, it would be sulfur. If we had 18 protons, that would be argon. And we're not exchanging protons by chemical means. We're not going to have an atom gain or lose protons because those are stuck in the nucleus really far away, a bunch of electrons in the middle. What we can exchange to make ions are electrons. So atoms can gain electrons or lose electrons to make ions, but this proton count, this is going to be constant for the atom, at least through chemical means. So we're not going to be changing the proton count through chemical reactions. Okay, so we have 17 protons for this atom. And then the difference between 35 and 17 is the number of neutrons, because the mass number is the sum of the protons and the neutrons. So if I have 17 protons, then I'm going to have 18 neutrons. So I can deduce from 35 minus 17 that we have 18 neutrons. And then in terms of the electron count, the charge of the proton and the charge of the electron just opposite of each other. So once we know the proton count, a neutral charged chlorine atom has to have that same number of electrons as it does protons. So we have 17 electrons to equal the charge and to balance the charge of our 17 protons. So 17 positive particles, 17 negative particles for a charged neutral chlorine atom. We'll talk ions in a minute, but we'll see that we can, gain an electron, lose an electron off atoms, and come up with plus or minus charged ions. Now, so what about having information like this? What if we say you have an atomic number of 26 and a mass number of 56? Can we work out the particles here? Well, we might just want to think how the periodic table might be involved. So element 26 is iron. So we're just like scanning for element 26. We get there with iron, so that's element number 26. And then we would write the atomic number. We often disclude writing the atomic number because it's kind of extraneous information. So you'll see a lot of times, like we did for chlorine, we just write 35 chlorine. We could write the 17 in right here if we wanted to. And sometimes you see this, sometimes you don't. But the 17 and the chlorine are extraneous information. They're redundant information. They're telling us the same thing. And same thing here. So 26 iron, we're just getting this off the periodic table. And then our mass number, if we wanted to write it, would be up here. And then we can take 56 minus 26. That gives us 30. 26 is our proton count, and then 30 is our neutron count. And 56, of course, is the sum of the protons plus the neutrons. So here we're going to have 26 protons, 30 neutrons, and then equal number of electrons. So whenever we say an atom with a charge, the atom has a neutral charge. So if we had an ion, the ion could have a charge that's not exactly equal to 0. So the fact that we're told atom here is how we're implying that our charge is neutral. So that the electron count would be exactly the same as the proton count. Yes. So the question is, will you have access to a periodic table? Yes. So for exams, you'll have the full periodic table. You'll see a sample info sheet that'll look exactly like exams that'll be posted midweek next week. But it looks very similar to the one. If you go to the daily quiz page or the recitation page, has a sample information packet with a periodic table. Like iron to Fe, sometimes that's a little bit of just making sure the name versus symbol versus name doesn't get us caught up on any examples, so we know where to look for information on the periodic table, but not for the entire periodic table. So maybe through the first 4 rows, some of the key groups are what I mentioned earlier for just making sure we know name to symbol, symbol to name. All right, let's talk about a couple ions. So when we introduce charge is just going to be obtained by exchanging electrons. So if we have Cl minus, this is now, and a lot of times when we start talking about ions, we're going to get rid of necessarily thinking about the mass number. If we want to know the mass number for a particular atom of a particular element, we have to know a little bit. Like, we can't just look at the periodic table. This gets into the weeds a little bit, but if you think about carbon, for example, we mentioned earlier, carbon exists naturally, 99% carbon-12, 1% carbon-13. That's not on the periodic table anywhere. I would just have to know that, and I just happen to know that. If I then say, what about iron? What are its common isotopes? I don't know them off the top of my head. I'd have to look that information up. But for the most part, the neutral particle, the number of neutrons in the atom don't really change a whole lot. They just change the mass of the atom a little bit, but they're not changing the positive to negative charge balance. Most of the properties of an element are coming from how many positive particles are there versus how many negative particles are there. So the protons versus electrons are really the primary thing we really want to quantify in an ion or in an atom. So unless we're given a mass number, we're probably not going to ask you about neutrons. So this question here is just asking us for the electron count. We could give the proton count too, because the proton count for chlorine would just be 17 protons. And then how do you think you end up with a net negative charge? So if you have 17 pluses and we're net 1 negative, then we must have 1 more electron. Now I could put an equation to this. I mean, I don't always like equations, but if you just think of the idea of charge, where charge is like the -1, that charge is being obtained by taking the positive particles minus the number of negative particles. So if we had 17 minus 17, charge is 0. So neutral if we have an equal count. And so if I know this is 17, and I know I have to get a charge of -1, then I have to have 18 electrons to get to an overall charge of -1. So if I take the positive charge minus the negative charge, it should give me the charge on the ion. Another way of thinking of this is just if you go from 0, so chlorine 0, 17 electrons, chlorine minus just picked up 1 electron. If we somehow had chlorine -2, we'll get to, probably not so surprising, one of the driving forces is obtaining a noble gas count of electrons. So like if you look at argon, in the entire noble gas group, the noble gas group of elements, they're not forming cations and anions. They tend not to bond with other things because they have a filled electron shell. So they completely filled all their available, sort of shells, if you will, with electrons already. They don't need to exchange electrons with other atoms through bonding or ionization. So they're happy as just monoatomic gases. Our other elements have to either bond or obtain electrons to come up with that count. So chlorine can pick up argon's count. Argon has 18 protons, 18 electrons. If chlorine picks up 1 electron, it obtains that especially stable count of electrons of 18. And so for chlorine to go to 2-, probably not going to happen. But if you said chlorine 2-, how many electrons would it have? It'd have 1 more electron. It would have 19 electrons. So you can think of just going chlorine 0, neutral, 17 electrons, negative adds 1 electron, -2 would add 2 electrons, -3 would add 3 electrons. And let's think of cations. So iron, we said before, or if we remember, that it's element 26. So we have 26 protons. And so to come up with a 3+ charge means that I must have lost 3 electrons. And so to have had 26 originally on a neutral atom means I'd have 23 electrons on iron 3+. Now, if you start wondering, well, what about the electron configuration? That's like chapter 6 and 7 later. So don't worry about electron configurations. If you're thinking 1s2, 2s2, that stuff, that comes later. We're not going over that material yet. And then another way, again, of using the equation would be if I get the +3, I'm going to get there by taking my 26 protons and then subtracting the number of electrons. And then so the number of electrons would be equal to 23. So you can come up with the 23 electrons either from an equation, which equations require us to remember the equation, how to use it. A little trickier, but I think it's much easier to think iron should have 26 electrons if it's neutral. We've lost 3, so we've gone down to 23 total. Now, lead's a big element, but it's still pretty easy to come up with the proton-electron count. So for lead 2+, we just need to know where to look in the periodic table. It's element 82, so it's in the carbon group towards the bottom. So it's element number 82. So that tells us we have 82 protons, and then I've lost 2 for 80 electrons. So hopefully pretty straightforward for looking at both atoms in terms of their subatomic particle counts. We just have to know a mass number. We're not going to predict the neutrons too easily without having information like a mass number or some information told to us. But we can predict the protons and electrons for any atom just given a periodic table. All right, let's look at a sig fig review problem. So why don't I give you guys a couple minutes. Now, sometimes you see a sig fig problem like this, and a lot of times this is the way the textbook asks these questions where they're kind of saying, assume these numbers are measurements. So anytime you see a sig fig problem where you don't see actual units here, you're assuming that each of these numbers is like a measured quantity number that's subject to the sig fig rules, and none of these numbers are exact numbers. So I like to put units on things so we know that things with units are measured quantities, but assume all these numbers are measured quantities. Give the sig fig problem a try. We'll go over it in a minute. All right, so let's take a look here. So for this problem here, one of the tricks is to not make the mistake, or one of the ideas is to not make this simple mistake. It's not to make the mistake that I see multiplication, I see 2 sig figs, so it must be 2 sig figs. That's not necessarily the answer. So that's not how I want us to think about sig fig problems. What I want us to think is that for the multiplication step, for this step here, just the 2.5 times the 0.295, where that equals the result shown here, the 0.7375, that result has 2 sig figs. So this number here should be rounded to 2 sig figs if we were reporting just that result alone. And so, or if we're then doing the next step, that's the last placeholder in that second digit, the 0.7375, 2 sig figs. And so I then look at what placeholder is that when I do the subtraction step. And so that's the placeholder happens to fall in the hundredths place, so my result should be reported to the hundredths place. So I do 12.67 minus 0.7375. I get 11.9325, and I round to the hundredths place, and that ends up being 4 sig figs. So hopefully you guys were on that track. Yes? Yeah, so should you round this here and then subtract or not round? For the most part, on an exam, you're not going to get a different answer. So if you had rounded it, you're going to still say 4 sig figs. This is like a tedious discussion of should you round or not round here. For the exam, if it's helpful for you, just round it to make this 0.74 so that we don't make a mistake. That's certainly a good idea. Where this comes into play is really in the lab, where you're going to do this calculation, then another calculation, then another calculation. There's a slight bit more significance in it being 375 than 400. So you could keep the 375 and then just kind of note the placeholder was that placeholder and then round to that placeholder later. So it's kind of like keeping an extra couple decimal places. So it's not going to hurt to keep the extra decimal places, probably more in lab. And I wouldn't let that get too much in the way of trying to get the right answer on a test question. Okay, so 4 sig figs for that one. All right, so let's talk a little bit more about the atomic mass unit scale. And this scale may not make total sense until we get into the next chapter. I think it'll make a little bit more sense once we see the mole on why it is that we're talking about AMUs. But whenever we talk about an atomic mass unit, when I talk about the mass of carbon being like 12 AMU, that's the mass of one single atom, like a very tiny atom. If you think of an Avogadro's number, if I had a mole of carbon, I think you guys have heard the mole unit, that would be 6.022 times 10 to the 23 carbon atoms in a 12 gram sample. So the mass of one carbon atom is an exquisitely small amount of mass. Okay, so the atomic mass unit scale, I mentioned this before, that 1 gram is equal to an Avogadro's number of AMU. So an AMU is very small, 10 to the 23. Just making sure I clearly write 23 here. And this I just write to imply that there's more digits we could know and write and use, but I'm just kind of like rounding it off to 4 sig figs here. So 1 gram, 6.022 times 10 to the 23 AMU. So an AMU is a very small amount of mass. So an AMU is like 10 to the minus 24 grams. And so the average atomic weight of an element, this is what we want to understand, is that the average atomic weight we see listed with each element is the mass of the average atom of that element in AMU. We'll see later in chapter 3 that we can also say it's the molar mass, that it's the grams per mole. We'll deal with grams per mole later, so don't let that worry you at this point if you don't know what that means. So the average atomic weight of an element, where we come up with this from is we have to take a weighted sum. So we get one of these fancy summation signs. So we sum the fraction of a given element, or a given isotope of an element, times the atomic weight of that isotope, and we sum that over all isotopes. So let's think about this for a minute. So what this is saying is you would take, for example, we see this here with carbon here, carbon 98.93% carbon 12. So the average atomic weight of carbon 12, or of carbon as an element, is going to be equal to this fraction here, because that's the fraction of one of the isotopes, and then that isotope's mass is 12 AMU. Now, there's some funny business here where this is actually where the AMU scale is defined. So carbon's mass is just defined by definition to be exactly 12 AMU. Okay, so this is just setting the conversion factor. This is like how you just define the centimeter to inches, 2.54 centimeters is an inch. This is just a simple definition. So we're just anchoring the AMU scale off the mass of the carbon-12 atom. So this is just simply how that AMU scale was devised. And you'll see later that it was very specifically devised this way so that things work out very nicely, so that you get a molar mass and a mass in AMU to be the same number. But we'll talk about that more later. But so then the weighted sum is then where you add, so summation, we add then another isotope, so carbon-13 is 1.07%. And so I'm just expressing the percent as a fraction. Percents are really fractions, they're just multiplied by 100. And so I'm just expressing 1.07% as a fraction, and then times 13.0034. Now you see carbon-13's mass isn't exactly 13 because now we have an actual measured mass in this scale of AMU. And so now that's going to be limited by how well we can measure a mass. And so we get that experimentally to about 6 or 7 placeholders experimentally known. And so then we also have a trace of carbon-14, but this is so small, it's not going to contribute to the average atomic weight. I mean, there's such a small fraction of carbon-14. And if you want to get into the weeds of carbon-14 for just a minute, it's an interesting element because you probably know, I've heard of carbon dating. And so carbon dating takes the age of a previous living object by how much carbon-14 it still has left. You may say, well, what is that all about? Well, when we ingest nitrogen into our diets, and we eat things that have nitrogen or take nitrogen in if we're a tree from the air, then the nitrogen has and one of its isotopes will eventually decay to a carbon-14, and then that carbon-14 will eventually decay to something else. And so from what we're taking in, that carbon-14 is depleting over time due to the natural processes by which that element's being created from like the food sources that we're consuming. So as soon as you stop consuming food, your carbon-14 starts to drop and eventually hits 0 in about 6,000 years. So you can date objects to about 6,000 years old using how much carbon-14 they have left. So just a little sidetrack on carbon-14, but it's a very, very minor trace. And so we're not going to worry about adding that into, and if we did, we'd see that it wouldn't contribute or change our atomic weight at all. And so we're going to add this up here. I could turn this into a sig fig problem. I'm going to, let's keep thinking sig figs through this example. So when I do 0.9893 times 12, the key is that 12 is exact. So I'm going to keep 11.87 AMU. I'm going to keep one more digit. I'll keep the full thing and just underline the 7 here. That I should have 4 sig figs here just from doing this math here. And then I'm going to do 0.0107 times 13.0034. So this mass here is 0.139. Let me do a better job of lining this up. So 13913. And so then this should be good only to the 9's placeholder, to the third digit in the number, because we have 3 sig figs times 1, 2, 3, 4, 5, 6 sig figs. So we'd round that one to 3 sig figs. So we have 4 times an infinite number of sig figs. So I didn't round the 12 times 9893 to 2 because 12 was exact. Okay, so I just kept the 4 off the 98.93. And so then when I add these up, I'm gonna round these to the hundredths place. So I have hundredths place plus thousands place. So I'd round this to the thousands place, or to the hundredths place, to the 7 placeholder in 11.87. So if I add 11.87 to the result, I get 12.01 is what I would round that to. So the average atomic weight of carbon is very close to 12, not exactly 12, because carbon's not 100% carbon 12. If a carbon sample is 100% carbon 12, then the mass of carbon 12 in the periodic table would be 12.0000 out to infinity, by definition, would be exactly 12. But we have a small amount that's carbon 13, about 1% of our carbon sample is carbon 13. We add that mass in. We're if you think of the mass 12 versus 13, we're bumped a little bit off of carbon 12. And there's some problems that get at this issue of, like, if you imagine an element has 2 isotopes and one mass is 12, one's 13. If it's 100% 13, then the atomic weight would have been 13. If it's 100% 12, it would have been 12. And if it's in the middle, it would have been like 12 and a half. So you can kind of get a sense of, if you know how many isotopes there are, what the average will be based on what the composition is. The composition means that if you look at a sample of carbon on Earth, that you're gonna roughly find every sample of carbon's about 99 to 1, 12 to 13. And so whenever you look at the abundances of the different isotopes, that if you took a random sample of those elements, you're gonna find that those percentages hold true. Okay, so then if we look at the periodic table here or on the wall or wherever, you can see that, for any element, you can just see that this value listed here, or this value listed, for whatever element you're looking at, is its average atomic weight, the average over all of its natural occurring isotopes and their fractions that they exist at on our planet here on Earth. Okay, so some elements like iodine, I circled iodine only exists as iodine-127, it turns out. So iodine happens to only be one isotope. And if you look at iodine, 126.9047, we can actually predict, remember how earlier I said you can't exactly get the mass number from the periodic table without more information? Well, if you know iodine's only one isotope, what isotope number, what do you think the mass number of iodine is? It's 126.9. The proton and neutrons are about a whole number, and it's not exactly the whole number. We can't exactly, if you recall, add up those masses because of the issue of the nuclear stability that the nucleus has. So that's close to 127. So you can predict here, once we know iodine's only one isotope, that this must be iodine-127 because that's closest to 126.9. So that looks like it would be representative of having 127 total subatomic particles that carry mass. So not a big detail, but if you know an isotopic mass of an element, like if you said, even if you go back to the iron example, we had iron 56 in the notes in a couple slides back, the iron 56, that isotopic mass would be close to 56 AMU, not dead on, maybe probably 55.9 to 56.0 in that range. So if you know a little bit of information, you can predict some isotopic masses. Okay, let's get into some group properties, because for the periodic table, we have some group trends that we tend to know. Like, one of the common trends is when we make ions out of these compounds, some of these groups of elements form this a very repeatable charge. And so the alkali metals, these form plus charged ions, so sodium plus, lithium plus, potassium plus. The alkaline group, they form plus 2 charged ions when they form compounds, so like calcium 2 plus, barium 2 plus. And then the alkali, the first group, and the alkaline, the second group, they only form ions with those respective charges. So only plus 1 for the first group, only plus 2 for that second group of elements. When we talk about all the elements in the middle of the periodic table, those are our transition metals. We'll see that, well, they're all metals, they're all metallic, but they do vary in their charge state. So we have a harder time just like looking at periodic table placement and predicting their charges. we'll see when we get to nomenclature that we'll come up with a nomenclature system to be able to tell you the difference between like iron 2+ and iron 3+. So we can't always predict on periodic table placement the charge, but you can kind of see that like potassium, sodium, if they lose 1 electron, they get that noble gas count. If calcium, magnesium, barium, if that group of elements loses 2 electrons, they get the noble gas count. So why it's +1, why it's +2, I think makes a lot of sense. The oxygen group is called the chalcogen group. So the oxygen group, these tend to form -2 charged ions when they make ions because they're 2 away from the noble gas group. Halogens tend to form -1 ions. And the noble gases are happy staying neutral, and they're happy not bonding with anything because they have that stable count of electrons already. There's also a similar set of properties in terms of how a group reacts, say, with water. So we can take a look at some of these reactions here. And this is probably not the most uncommon demo. Is that your like alarm to wake up to?
Yeah, I have a very hard time waking up to
I would imagine that would wake your whole dorm room up. Let me ask you this: how many of you guys wake up to like an Apple Watch buzzing? Can any of you guys wake up to that? Has anybody not tried like using their watch? If you have a watch, set the alarm sometime. I mean, when I use that every morning, and when it goes off, I mean, I am up. For some reason, like my wrist buzzing just like really wakes me up. Okay, so we'll look at this demo here. So I always find this funny, like on how I suit up and I'm supposed to do this, and you guys are like almost as far away as I am. So if you feel uncomfortable, you're more than welcome to scoot back, but I think we're perfectly safe here. Okay, so what we're gonna do here is we're gonna add, let me switch the screen over. Okay, so we have water, and I have lithium to add into the water, sodium, potassium, magnesium, and calcium. And so let's see what we come up with first. So that's magnesium. We'll do that last or next to last. Sodium, lithium, potassium's the fun one. Calcium. And then they give me some indicator. I'm going to assume they already put the indicator in, but we'll see in a minute if they haven't. Okay, so let's start with lithium. And so lithium is the 3rd element on the periodic table. It's in the group of elements that forms a +1 ion. And it's really, we're going to see, probably reactive with water. So let me get a little. Oh, they didn't actually put any of the water in yet. Well, this is the opposite of what you're supposed to do. This should be fun. All right, why did that not? Oh, I think I'm supposed to rinse these off too, possibly. All right, well, that was supposed to react. Let's move on to sodium real quick. That's either mislabeled or like it's like coated in a like mineral oil that needs to, as soon as that mineral oil layer gets broken through, it'll go. So there it goes. So like this, so these metals are stored in like a mineral oil, and we just got to, as soon as we penetrate through the oil layer and there's a little oxidation layer on the metal, as soon as we get through that, then you see the reaction kind of start to take off. Well, let's be bold. I got a big piece of sodium here, and I guess I should add the water. Let me add a bunch of water here to these. So there goes sodium. So what we're seeing is lithium reacted maybe not as violently as sodium is, but still reacted with water fairly readily. I have one of these screens just to make sure it doesn't go flying out at us, but I don't think it's going anywhere. Potassium's going to be the fun one. So if you get a little bit of a trend, it's that lithium reacted, sodium reacted in a similar way but a little faster. And let's see if we continue that process with potassium. And you might expect potassium's going to be a little bit more interesting because we have a bigger container. And we'll see that there's probably a good reason for that here. Okay. Got a piece of potassium. You can see what's going to happen since I'm really getting ready for this. And so it actually lights on fire and reacts in a similar way. So what's going on here is, and in terms of the chemistry, we don't get so detailed here of like writing out the actual steps of the reaction, but what's going on is we just have the metals forming their ions. So lithium's going to lithium plus, sodium's going to sodium plus, potassium's going to potassium plus. But what's going on at the same time is that in the water, we have the hydrogen and water turning into H2. So we're creating hydrogen gas along with these reactions. It's doing an oxidation reduction reaction. So if we have a metal being oxidized, we have the hydrogen being reduced to H2. And then we see the reaction is exothermic enough for potassium that it actually ignites the hydrogen. So that's what the flame's coming from, is actually that reaction being hot enough that we get to the point where we actually ignite the hydrogen. The other reactions just didn't give off enough heat in order to ignite the hydrogen from the quantity that we had done. Okay, so one last set of reactions is to see that fundamentally the, that the alkaline metals react a little bit differently. I can also have added an indicator. Let me add a quick indicator to the 3 that I've done so far. What this indicator is showing is that we have hydroxide ions that have been formed. And so it's showing the presence of a basic solution. And so the byproduct that we're basically forming is lithium hydroxide, sodium hydroxide, potassium hydroxide. And I'm going to add a little indicator in so that if we form that with the next metals, we'll see it as those metals react, if they react. So I'm going to take a little piece of magnesium. I'm going to add that to the water. And so you can, but since I added the indicator, I don't know how well you can see it on the screen, but up front you may have seen a little bit of a quick reaction of a pink color. And so magnesium reacts, it's just not as fast, and then it sort of was dissipating the relatively quickly. And if we do calcium, we'll see if it continues the trend of reacting a little bit faster than magnesium. And so, again, on the screen, I don't know if you can see it, but there's a little bit of a pink color that's emerging. So I can see the solution turning pinkish slowly. So the alkaline metals, they're forming the +2 and the -2 ions. They're just doing so not as quickly. So they're reacting, but with like a different trend. And so what we're seeing is just the periodic nature of the elements, in that our first column of elements react very similarly to each other, with maybe an increasing trend of reactivity from top to bottom. And then also we're seeing the alkaline group react a little bit differently, not as violently, but maybe still with more of a pink color for calcium, so still being the same trend that we're getting a little bit faster towards the bottom. A couple other periodic trends to note, that the halogens are a really interesting set of properties where this is chlorine, so chlorine is a gas at room temperature. Bromine is a liquid at room temperature, and it's also a vaporous liquid. You can certainly see a gas in the container, but there's a liquid at the bottom. I think at least those down front can probably see the liquid bouncing around the container. So bromine has a melting point, or excuse me, a boiling point just above room temperature, and then iodine is solid. You can see solid at the bottom of the flask. It also gives off a vapor. You can see like a pinkish vapor inside the container. And so there's a couple things we can do. One, I can take bromine and freeze it out. And so I can actually put this in liquid nitrogen. So I'm going to do that. Let me this liquid nitrogen up to 77 Kelvin. And so when I add this flask, glasses on. How many of you guys were thinking that? Just one. There we go. And so now when we put the bromine into liquid nitrogen, it's going to freeze out that vapor. So the vapor is going to do what water would. It's going to condense. And so the vapors are going to condense. We're going to see that just after a second or two, that we've kind of like frozen out the bromine. So we're just freezing bromine, and its vapors depositing as a result. So the vapors that were inside the container are depositing. And so we're just, by changing the temperature of bromine, we're just going through a phase change, and we're just seeing the vapors condensing and then freezing into their solid form. One quick aside would be that, like, one of my memorable song is that "Sippin' on Straight Chlorine" by 21 Pilots. This is one of those three you can sip on. None of them. So I would recommend drinking any of those. But you can't, I don't know why he wouldn't have chosen bromine in this song, because you actually technically sip a liquid. The lead singer of 21 Pilots went to Ohio State. I don't think he took my class though. But I just want to find that bromine would have gone with that too. Okay, so there's something fun you can do with liquid nitrogen. That is, you can take this is ordinary racquetball and freeze the racquetball. So there's a racquetball in here too that's been in here for a while. And so now the racquetball just, the material freezes in it and then becomes hard. And what can you do with that? You should be able to snap it. So if I just throw this in the ground, you should be able to smash it. All right. I haven't done that one in a while. So if you want to do that, chemistry, you can do that. Smash a lot of stuff with nitrogen. And so then the last thing you have to do is that I was doing this too, is that the nitrogen is just so liquid nitrogen, 77 Kelvin, what it does is it boils. So it's just boiling into the vapor, so it's going from liquid phase to the gas phase really quickly as we just throw it in the room and let it warm up really quickly. So we're just seeing that phase change take place. Okay, so with that, let's get into a couple other things we can wrap up for the chapter, or for today. Okay, so hopefully we're just seeing the periodic nature that what really gives a group of elements a similar property, of course, is the row that they're in, the column that they're in. The row is a varied set of properties. If you look at sodium and across to magnesium to aluminum, silicon, all the way to argon, you're going from metals to metalloids separating the metals and the nonmetals, to then nonmetals on the far right side of the periodic table. So you have a big difference of property from left to right, and a very similar set of properties from top to bottom. So when you're looking, I'm going to see if there's a periodic table nearby, but if you're comparing properties, chlorine is going to be more similar to fluorine and bromine in its properties than it will its neighbors of like sulfur and argon. So more similar here, and then less similar as you go from left to right. So big differences left to right, smaller differences top to bottom. Now, how do we determine, if you go back to like the problem where we were determining the average atomic weight, how do we determine those? Well, we determine those using something called a mass spectrometer. So a mass spectrometer, what it's able to do, it's able to detect, the ratio. Like this is the experiment we would do to determine the natural abundance of the isotopes of a given element, such as chlorine. So chlorine's about 3-to-1. So it's about 75% chlorine 35, it's about 25% chlorine 37. And so that's just for chlorine. What its makeup is kind of just like how for carbon, it was 99-to-1, carbon 12 to carbon 13. So here we're about 75%. Why did that change? So 75% carbon 35, and about 25% chlorine 37. Now again, you wouldn't have predicted this without knowing this or looking this up or determining that from an experiment. And then also for chlorine, that these are the two isotopes that exist naturally. There's no other isotopes of chlorine that turn out to exist in a natural sample. So if I said, without looking, what do you think the average atomic weight of chlorine is? Well, this mass is about 35. This mass is pretty close to 37. And a 50-50 ratio would have put the average rate at 36, 100% ratio rate at 35, 100% ratio 37, rate at 37. So a 3-to-1 ratio, probably about 35.5. So if you look at chlorine on the periodic table, it's 35.453. So kind of like right where you would expect, kind of a little bit closer towards 35, but not dead on 35.0. And so the prediction of the average atomic weight of chlorine, we'd say probably about 35.5, and then its actual average is 35.453. And so you can kind of get a sense from that ratio that it's somewhere between 35 and 37, and the weighted average puts it right at about 35.5. Well, if we look at bromine, so bromine's over here. So this is bromine 79, and this is bromine 81. Those are the two isotopes that naturally exist for bromine. And so now for bromine, knowing that it's only these two isotopes, so a mass spectrum would show us all the ions, or all the isotopes that exist for a given element, and also from their peak heights gives us roughly the average. Here, this is about 50-50. It's about 1-to-1, an equal ratio. And so the mass of 79 bromine would be close to 79. The mass of 81 would be close to 81, not dead on, probably talking 79.9 versus 80.9. So the mass here is probably about 78.9 here, and about 80.9 would be roughly those atomic weights for those isotopes. So what do you think the average atomic weight of bromine would be without looking at the periodic table? I would predict it'd be about probably 80. You know, maybe if you say the isotopes are starting to not be dead on the whole number, maybe 79.9. If you look at bromine on the periodic table, it's 79.904. So we can, easily predict with some information. We could calculate with more precise information. If I give you the precise atomic weights and the precise ratio, we could very exquisitely just apply the fraction of the one times its atomic weight plus the fraction of the other times its atomic weight and calculate that very precisely as well. Interestingly, bromine forms that molecule Br2. If you look at a mass spectrum of Br2, it's kind of interesting, I think, to think about how bromine 2 as a molecule, if you think of bromine, it's like you could have 79-79, you can have 81-81, or 79-81, 81-79. You can have all three of those combinations, and the most likely combination is where you have a mix of one mass and the other. If you just think, what are the odds that I have, if I have a 50-50 chance of either isotope? I could have 79-79. I could have 79 bromine, 81 bromine. I could have 81 bromine, 81 bromine. Is that like the coffee shop blender that I just heard? So we can go 79-79, 79-81, 81-81, 81-79. And the idea would be that, what did I do? Where did my writing go? I don't know what I did that made my writing disappear. But so roughly you'd have 50% chance of this one being 79, 50% chance of the other one being 81. And so it ends up being more likely that you're going to have the 79-81 because you have two possibilities for that one. One possibility for the 79-79, 81-81. This is the 79-81, the 81-79. Not a big detail, but just kind of how you can make sense of a mass spectrum of something like Br2. So the way the mass spectrum works is you actually put a charge on the ion, then you bend the ion with a magnet. So you're kind of doing that magnetic wand trick that we were doing with that cathode ray tube experiment, but with a beam of actual atoms now. And you're just seeing how much they bend in a magnetic field. So mass spectrometry, very, very basic technique. You don't have to really understand it too much in terms of what's going on. I think the key detail is that mass spectrometry, that technique, is how we determine precisely the atomic weights of the different isotopes. We can use that to determine molecules, molecular weights too. And we can also use it to determine the ratio of the ions. So we can use it to determine the ratio of the different isotopes of an element with that technique. So it's just how we get some of the numbers and data that we present in atomic weight problems. So just the periodic table again. So what I hope we walk away with is just a greater understanding of what it means to know the average atomic weight. And then we can use that, and we'll use that a lot for like molecular weights and molar masses as we get into chapter 3 later. So when we're coming up with the average weight of like a molecule, if we had like water, we'd be taking this mass. So for water, 2 times the hydrogen plus the oxygen mass. And that would be the mass of like an average water molecule. So we'll use atomic weights more in chapter 3 to quantify aspects of molecular properties. So I think the last thing for today is just kind of like starting to picture representations of molecules either being through formula. So CH4 for methane, we have a structural formula. We can show how those atoms are connected together with something like a Lewis structure. We can predict the actual shape of the molecule in 3 dimensions. These 2 tasks in terms of predicting them are chapters 8 and 9. So you don't have to see a structure here in chapter 2 and predict a Lewis structure. You'll learn how to sketch those Lewis structures when we get to later topics. And then we can also picture things through ball and stick models or space filling models to get a sense kind of sort of the size that these atoms are occupying. And so what's important for a molecule, so when we look at molecular compounds are compounds of non-metallic elements. So things like hydrogen, oxygen, carbon, nitrogen, the entire halogen group, sulfur, phosphorus, those molecules, those atoms, when they interact together, are going to form non-metallic compounds. They're going to form what we call molecular compounds. They're going to share their electrons. This is shared electron bonding. We call that covalent bonding. This is different in nature from the type of bonding we see in something that's ionic, where we have the electrostatic force of attraction of plus and minus. So ionic compounds are metal, non-metal. Molecular compounds are forming from non-metallic elements sharing their electrons through covalent bonding. Now, the issue here for molecules is that we really want to know the molecular formula. The molecular formula is what tells us, something about one molecule. So if I have a sample of methane, I would have a bunch of molecules that just have the formula CH4, and each one of those molecules are separate from each other. Kind of like how if I had a sample of argon, I'd have an argon atom here, argon atom here. I'd have a bunch of argon atoms that are individually separate from each other and not really bonded together. If I had a sample of methane, I'd have a bunch of molecules of methane that are all separate from each other and bonded together. Well, if I look at a compound similar to methane is ethane, we'll learn how to name this systematically a little bit later, but C2H6 is ethane. And then ethane kind of looks just like the methane does. In terms of a 3-dimensional shape, I wouldn't worry about necessarily you yourself sketching the shape here, but just trying to show that we have a CH3 group and another CH3 group, and so we have 2 like CH3 groups that are bonded together. Now, it turns out carbon likes to form 4 bonds. If you take that lesson, we'll repeat that a bunch of times. We'll show you a bunch of examples. Carbon forms 4 bonds, 4 single bonds, 2 double bonds, a triple and a single bond, but never anything more than that in a stable compound. And that'll get you through a lot of OChem, just making sure that you don't show 3 or 5 bonds to carbon. But carbon likes to form 4 bonds. So C2H6 is a molecule of ethane. Now, that's what's important for ethane, is that C2H6 or CH3, or that it has all these bonds connected together in that kind of fashion. If you then said, well, what's the empirical formula? What's the simplest ratio of carbon to hydrogen? The empirical formula of ethane would be CH3. And that doesn't really tell us anything. There's almost no significance to an empirical formula, other than in the next chapter, you'll see that from experimental data, we can determine an empirical formula, and with more data, we can determine a molecular formula. So later, you kind of get to see that when we're trying to figure out what is the formula of a compound, one of our processes will be, well, let's get some information that get us an empirical formula, then a molecular formula. But the empirical formula itself, there's nothing unique or special about C2H6 being CH3 empirical, but you can say the simplest ratio of carbon to hydrogen in C2H6 is CH3. It's a thing. It's an empirical formula, but there's not much information. When 2 compounds share an empirical formula, that's almost nothing of significance. Acetylene and benzene share the formula of CH, 1-to-1, carbon to hydrogen. They share almost nothing in common with each other. So two compounds share an empirical formula doesn't mean anything. There's nothing special there. But an empirical formula is just the simplest ratio. The molecular formula is exactly how many there are in one molecule. All right, guys, we'll pick up from starting to name compounds and different classifications on Wednesday. Enjoy the weekend. Go Buckeyes. Who's going to the game? Have fun at the game if you're going.